Morning. At the end of last class, we were partway through an example about 2-3 tree insertions. We were adding numbers in order, and we found that doing the same thing on a binary tree would cause catastrophic results. Any operations on this binary tree would take asymptotically longer than a 2-3 tree that has the same content in the same order. And that's a big deal. The rest of this lecture just keeps on inserting things. And the lecture after that talks about the delete operation. Both are pretty important, probably. But at this point, you already know all that you need to know about 2-3 trees to do the associated question in the assignment. So I'm going to skip ahead a bit and talk about priority queues and heaps, because I just want to get you all to learn all the stuff you need for the assignment as soon as possible. We could get back to 2-3 tree insertion examples and how the delete operation works later. And I'm probably going to introduce graphs a bit earlier for the same reason. Sorry for jumping around, but I hope that the disorganization is for your benefit since it introduces assignment concepts more quickly. So let's talk about priority queues. I sort of alluded to this. Oh, wow, 2 questions. Who of you put your hand up first? Yeah, cool.
Are we going to be testing on the delete operation?
Only if I cover it tomorrow. So, the quiz will follow the same, very general structure as usual in that it'll cover material up until Wednesday's class. So, whether or not 2-3 tree deletion appears on the quiz will depend entirely on whether or not 2-3 tree deletion gets covered in Wednesday's class. And you had the same. Where was I? Oh yeah, so I sort of alluded to this last class, but this ADT is called a priority queue. A classic example of where it would be used is a hospital waiting room. Patients with more severe conditions get treated first. They are prioritized over others. So it's similar to a queue. In fact, I suppose you could say a regular old queue is an instance of a priority queue where the priority is defined as the order in which elements were inserted. Sure. But it has 2 main operations. Insert acts exactly as you'd expect. It inserts a new entry into the queue. And then retrieve max removes and returns the item with the highest priority. So the hospital patient who's doing the worst. There can be priority queues based on ascending order and descending order. In this class, we're basically just going to be dealing with max priority queues, in which higher numbers represent higher priorities. But it doesn't take much generalization to figure out how all these ideas would apply to queues where lower numbers mean higher priorities. So take a moment to think about how we would construct a priority queue using the data structures we know right now, and think about what the implications of those choices would be, mostly in terms of the time complexity of those operations. we already know quite a few data structures at this point. Let's see here, linked lists, binary trees, balanced trees, and hash tables. I'm not going to go through all of these, but I will mention sort of the easiest implementation I could think of, which is using a sorted array or linked list, where insert would just put a new item into the appropriate position in the list based on its priority, and then retrieve max would remove and return the first item in the list. For the sake of an example and keeping it simple, I'm going to go with a sorted linked list, because then inserting into the middle of it will be a lot easier than with an array. So I'll do sorted linked list. So how long would it take to insert something? You'd have to go through the linked list, check each element's priority. Remember that those linked list nodes might contain other data, but we're just checking priorities because that's what it's sorted based on. Sort of like making an inventory and only checking names of fish, even though fish have other properties. So you would go through the linked list, check each item's priority, and then insert the new item in the place it should be based on surrounding items' priorities. Worst case scenario is if this new item is inserted at the very end, it is the lowest priority item, and you had to check all n items in the linked list. So it's O of n. Retrieve max fares better, however. All the infrastructure I've been setting up has been leading up to this. With a sorted linked list, hopefully it's sorted in the right order such that the item with the maximum priority is at the beginning of the list, which you can just pluck from the list in constant time. And before moving on from a sorted linked list, I just want to do one more example. Say you have an unsorted linked list. Can I just copy stuff? Actually, I'll just write it out again. Partially because I don't feel like figuring out copying and pasting for this app, and because you're probably following along. I want to give you time to write this stuff. So if the list is unsorted and you're implementing a priority queue, you could just insert stuff right plopped into the beginning or end of the list, constant time. And to get the maximum element, you would have to go through the list, checking all the priorities, and return the highest priority value you found. Since you go through all of the elements once, it ends up being O of n. As a side note, even though this sort of thinking isn't really assessed in this course, I think it's the most important part. I probably talked about this before, but when you're in the real world and actually making new things, you're going to be faced with a lot of decisions about how exactly to implement the functionality that your boss described. And being able to think through examples like these and figure out the time complexity of different operations without writing a single line of code is super important for the planning process. But anyway, this lecture is kind of about priority queues, but it's really about introducing a new data structure that's really good at implementing priority queues. And I feel like this is kind of similar to what we saw with binary search trees. We have a situation where all of the data structures we know give us some sort of trade-off. With the linked list examples here, a sorted linked list would have a slow insert but fast retrieve max. Unsorted linked list would have fast insert but slow retrieve max. And this new data structure, the heap, will give us still pretty darn fast time complexity for both operations. It's more balanced. It's all around good. Quick diversion. You know binary trees. You might remember perfect binary trees where like the tree has a maximum number of elements for its height. This is a related definition. You don't have to memorize it, but it's a useful word to introduce because we're going to be talking about complete binary trees. A complete binary tree is a binary tree in which every row except maybe the last one is full, and all entries in the last row are arranged as far to the left as possible. So if I added an element like this, that would still be complete because every row except possibly the last one is full, and all elements or all entries in the last row are arranged as far to the left as possible. If I added a node here, then this would not be complete because to make it complete, this should be further to the left. And if I deleted this node, then it would still also be incomplete because not every row, except maybe the last, is full. I'll give you all a moment to copy this down, just writing down what I was saying about whether or not the binary tree would continue to be complete based on certain node additions. Geez, when is it going to actually introduce heaps? Okay, next slide. So if a complete binary tree contains n entries, then the height of the tree is less than the base 2 logarithm of n. This inequality can be used to prove that the height of a complete binary tree is O of log n. So yesterday we talked a bit about how important it is to balance a tree. And this slide is basically saying that a complete binary tree is always balanced. So if we can make sure that our data structure is always a complete binary tree, we guarantee that it's always balanced. Now for the heap. Kind of similar to a binary search tree, but don't get these confused. A heap is a complete binary tree whose entries are arranged in heap order, where the value in each node is greater than the values in its child nodes. So remember that like the binary search tree property had nodes arranged such that the nodes on the right were greater than the node in the center, and the nodes on the left were greater than the node in the center. This is slightly different. Now, the nodes in the parent, or node value in the parent, is always smaller than the values in its children. Yeah?
The other slide, the very last sentence, it says the height of a complete binary tree is O log n.
Mm-hmm.
That's just log n.
Oh, like, are you talking about the lack of a base here?
No, I'm talking about why is there a big O if we're talking about the height.
Oh, okay. What answer can I give other than like, yeah, it just is? Well, if you made a formula for the height of the tree based on n, it would kind of be clunky because it would be something that only increments by 1 when you double the n. But anyway, if you made a formula for h, then you would be able to prove that that formula for h is in big O of log n. Does that make any more sense than the slide? Kinda, sorta. I don't know whether this will be any help whatsoever, but this is very similar in spirit to the assignment question about 2-3 trees, where you show that the height of a 2-3 tree is in big theta of log n. Basically showing that if you make a formula for the height, then you will be able to prove that that formula is in big O of log n, or big theta, or whatever. Whoosh. So, heap order. The value in the parent needs to be greater than the values in both of its children. 60 is greater than both 57 and 45. 57 is greater than both 52 and 48. 52 is greater than both 42 and 12. I won't make all those comparisons. They're all true. Every node in the tree follows this property. Yeah, even the ones that don't have children technically do follow that property. The value in each node is greater than the values in all 0 of its child nodes. This is a bit simpler than the binary search tree property, actually. And also note that the order of children doesn't matter. We could have a heap that goes like 60 and then 45 on the left and 57 on the right. And that would still be a heap. It wouldn't be a heap if you swap these values around in a way that satisfies the binary search tree property. That's not a heap. That's no good. That's a binary tree, and we've mostly moved on from those. Clarification that I'm excited to give is to do with something that you might have learned about in a course like Comp 2160 that talks about the memory architecture of a typical computer. Like this is just an unrelated yap if you haven't taken that course, but if you have, you've heard about the two main memory locations on a computer, the stack and the heap, where the stack is like more organized and manages itself automatically, and the heap is just doing whatever you're responsible for it. The stack, like the stack, is a stack as in the data, or as in the ADT that we learned about in class. They are related. The stack that you learn about in Comp 2160 involves pushing and popping things to it. The heap, on the other hand, has nothing to do with this data structure. The heap in your computer's memory management, where you can dynamically allocate memory and then you have to make sure to free it yourself, that has nothing to do with a complete binary tree whose entries are arranged in heap order. So the stack is a stack, the heap is not a heap. It's weird. I think that they might have just coincidentally gotten the same names for the heap and heaps because they're both kind of disorganized. Like you could imagine values just sort of piling up in this tree and data being super disorganized in the heap. But I just think it's a cool detail, kind of cool. And I wanted to mention it to prevent any confusion. Don't think about the heap as in Comp 2160 when you're thinking about heaps as in Comp 2140. Heaps are pretty interesting in their implementation. The way we're used to implementing binary trees is using a linked data structure. This is a generalization that you might not have thought of before, but anything involving pointers or references, I like to call a linked data structure. Linked list is the simplest linked data structure you could think of, but a binary tree where there would be a node class with left, right, and maybe parent pointers, that's also a linked data structure because it's linked to other instances of itself. And think of why that's useful. With a typical binary tree, you would be pretty uncertain about like what links actually exist. Yeah, this is fine. Wait. Yeah, sure. I think this illustrates my point. You would have some uncertainty about what links exist. Like, this root node is not guaranteed to have a left child. So if you don't know whether or not it's going to exist when you initialize the data structure, there's no point in allocating memory for it ahead of time. It's better to just make nodes as you need them. However, with a heap, this thing is always going to be a complete binary tree. We always know that the nodes are going to be arranged in a certain way that is very packed together and nicely space efficient. So that kind of frees us up to make assumptions about how this is going to look and make some implementation decisions that might not have made sense with a generalized binary tree. The implementation decisions in question we're going to use an array. So the heap is going to be stored in an array where the array indices correspond in a nice and convenient way to positions in the complete binary tree. This does have the disadvantage of how arrays need to have all their memory allocated up front. But as you probably learned in Comp 1020, there are ways to resize an array dynamically, basically copying the heap into a new array of twice the size. I want to get to like how the entries are actually stored in the array as quickly as possible, but it's probably worth mentioning this beforehand. Since the heap occasionally has to be resized, this means that some insert operations can be more expensive than big O of log n. If you just happen to fill up the last array index and you know that you have to copy the array into a new one, that'll involve copying every element individually. That'll take O of n time because you need to do something for every element in the array. However, for reasons that I'm going to hand wave right now, though I'm getting total deja vu. I had to talk about this before. For reasons I'm going to hand wave right now, this doesn't change the time complexity. Not even really when you're talking about the worst case. The times when you have to resize the array, like copy all of its elements into a bigger one, when inserting happens so rarely that it still makes sense to say that the time complexity is always big O of log n. The reason why this works mathematically and not just, this doesn't happen that often, we could just disregard it, is thanks to a technique that you might learn about if you take the course Comp 3170, Analysis of Algorithms and Data Structures. The thing's called amortized analysis, and it's a way to formally mathematically prove that even though insert operations will occasionally take O of n time, they still take O of log n time on average. And it's pretty neat. Okay, so now for how we store the entries in the array. And also at this point, I think the advantages of using an array, if we know the binary tree is going to be complete, isn't really obvious yet, and might never be, but I hope this justifies it. So we're going to store the entries of the binary tree in an array, basically just row by row. The root element is going to be at index 0, and then the first element of the next row is going to be here, and then the next element of that row is going to be right here, and then this entire row is going to be the next 4 elements. And you can probably imagine how the rest of that is going to go. And I guess that with this specific size of array, inserting another element would require you to resize it, but don't worry about that. amortized analysis says that you don't have to worry about that. So why use an array this way? Well, one advantage is that the largest entry in the heap is always the first element. Recall that we're motivated to look at heaps for the sake of finding an efficient implementation of priority queues. So we already know that we're able to find the largest entry in the heap pretty quickly. And that's kind of cool. You can still find the largest entry in the heap quickly with a linked data structure for a binary tree. So if I were you, I wouldn't be convinced yet. But then the real big advantage of using arrays, I think, is that now that we're using an array to store the tree, we can take advantage of how arrays offer constant time access by index to access any element of the tree in constant time. So like, trying to think of an example. This is contrived. It doesn't necessarily follow how you would use heaps, but let's just say I wanted you to find the right child of the left child of the root. So that's this node. If you were doing this on a binary tree implemented using a linked data structure, you would have to follow the left child of the root and then follow the right child of that node. That would be two different pointer accesses, like root or current equals root.left, current equals current.right. That's all well and good, but for reasons that you'll learn about in future courses, that is slow. It's stuff that doesn't really show up in the more theoretical cost analysis that we're doing in this class, but it's still worth knowing about. Basically, accessing two pointers takes forever when you could do some pretty clever math on these array indices and go like, oh, right child of the left child of the root, that is this one. Using only one access to the array and a bit of math instead of two pointer accesses. So yeah, I think the reason why we don't always use arrays to store trees in all cases is because of what I said about potentially wasting memory. Like, if I had a tree that looked like this, and I was storing it in an array, let's see. I'd be wasting all the memory that would be dedicated to storing these nodes. So using this strategy isn't necessarily a good idea for storing binary trees in general because of potentially wasted space. But if you know that your binary tree is going to be complete, then you know that you're going to be using all indices of your array, like there won't be any gaps. So then you could take advantage of constant time array access. Yeah?
Howard,
Yeah, and I recall, although I don't think I mentioned it, that values can indeed have the same priority.
So how would that
Uh.
be stored in the
Kind of unsatisfyingly. Definitely simpler than you might think. And in fact, I think I might dodge the question entirely because we're going to learn about how entries are inserted into heaps. And I think learning about how the heap insertion algorithm works will answer your question about duplicates, how duplicates are handled. Because the answer is just, it gets inserted like anything else, and it just works. So yeah, good question because it covers stuff that we haven't really considered yet, so stay tuned. So I mentioned that you could basically do any traversal, kinda, of the tree. You could access any element of the tree in constant time, just because arrays let you access any element of the array in constant time. But how exactly is that going to work? How did I just pull out of a hat that the right child of the left child of the root is going to be at index 4? Well, there are some simple formulas, and they have a pretty neat connection to the fact that this is a binary tree. But first, let's just take a look at how these are arranged and try to guess at what those formulas are before I formally define them. So we have the root node 60 at index 0. Its left child 57 at index 1. And then what about its left child? It's not at index 2, but it's at index 3. Wondering if I should look at a different side of the tree to make the numbers look nicer. Just give me a moment. Nah. The patterns will be the same no matter what. So we're at 52 at index 3. What about 42? Where is it? 5, 6, 7, 8? Wait. 4, 5, 6, 7. Okay, phew. And then its left child, 16. Oh, geez, this is going to be a lot of counting. 8, 9, 10, 11, 12, 13, 14, 15. Hey, remember that time when I was talking about height of a binary tree and I was trying to find a pattern in how many nodes the tree could have based on its height? And the progression kind of looked like powers of 2, but not quite. Well, 1, 3, 7, and 15 sure remind me of 2, 4, 8, and 16. As you go down this side of the tree, the indices seem to double. Now let's go down the right side of the tree as well. So the right child is going to be at index 2. Right child of that is going to be at index 6. And then 14. Still kind of doubling each time, but the connections to powers of 2 aren't quite as strong. So it's a bit of a mystery how this is actually going to work. I'm not sure what other examples to go over before just telling you what it is. I'm not sure how to pretend that we're discovering it ourselves, even though that's the most fun way to learn math. Yeah, whatever. I'm tired. You're tired. Let's just see the answers. For an entry stored at index I, the left child is stored at index 2i plus 1, and the right child is stored at index 2i plus 2. Ignore the thing about the parent for now. So let's get the left child of 60 again. 60's index is 0. 2 times 0 plus 1 is 1. That's 57. Now let's get 57's right child. Nothing significant about left child versus right child here. I'm just choosing random examples. The formula for that is that the right child is stored at index 2i plus 2. So 2 times 1 is 4. That plus 2 is 6. So we know that this node will be stored at index 6 in the array. Let's go to this node. 2 times 6 plus 2 is going to be 14. Then I'm pretty sure this math is right. 7, 8, 9, 10, 11, 12. Oh no. Oh yeah, it's because this is obviously not 6. Hold on. Oh yeah, 2 times 1 plus 2 is 4. Duh. Hope no one had their hand up while my head was just buried in the iPad. Okay, and then that will make the arithmetic for accessing the node of index for node 48. Makes sense? 2 times 4 plus 2 is 10. Wait. Hold on. God, this is not my day for... Okay, 2 times 1 plus 2 is 4. We got this. And then 2 times 4 plus 2 should be 10. So this should be index 10. 5, 6, 7, 8, 9, 10. Phew. Now let's try out that formula for the parent. Let's say we have node 39 and we want to access its parent. Let's see, that 5, 6. 39 is at index 6. And then its parent will be stored at the floor of I minus 1 divided by 2. hopefully you're familiar with the floor function from assignment 2, but just in case you need a refresher, this rounds a rational or real number down to the nearest integer. So six minus 1 over 2 is going to equal 5 over 2, 2.5, 2. So the parent of 39 should be at index 2, which it is. Amazing. So I hope this demonstrates how you would navigate the tree by calculating array indices as an alternative to navigating the tree by following pointers. You could also start to think about how this might also be a lot more space efficient than a linked data structure for trees, where a linked data structure for a tree would involve a bunch of node objects, each of which have a node pointer for its children and maybe one more node pointer for its parent. This just stores the data directly in an array. If you're using a low level enough language, there's no other data stored auxiliary to the array. It's just a bunch of values. So you don't have to store all those references. So I hope you could see how, if you're storing like a humongous heap, storing it as an array would save you some space because you don't need all those pointers. Okay, let's check out insertion. As we do all these operations, we're going to assume that the array that stores the heap has room for a new element. That's just because it would be really annoying to repeatedly say, if the array is full, resize it at every turn. Remembering that the array needs to be resized occasionally doesn't make the problem any more interesting, just makes it more tedious. So we're going to assume that we always have space. So let's insert 50. It's the easiest thing ever, at least the first step. You just put it in the next available space in the tree. Because the binary tree is complete, this corresponds to the earliest available array index. However, this will almost certainly break heap order. Let's see. Yeah, it sure does, because 50 is greater than 30. 50 should be up here. Why'd we screw up so bad? In order to fix the heap order, we're going to check whether the parent priority is smaller than the new priority. And if it is, swap the 2 entries and repeat. So it'll be something like if array at index I is greater than array at index whatever formula we use to find the parent, don't feel like rewriting these array indices. Whatever. Something like this applied to array index I right here. And like I've been saying, this is functionally equivalent to going like, if current node dot value is greater than current node dot parent dot value, swap those two values. But again, for reasons that you'll learn about in later courses, array access is way nicer than pointer access. So this is nicer for the computer. So we swap the two entries. 50 is now in its rightful place because it is like, it's in heap order. Its children are less than it. However, this doesn't completely fix things. It is still not in heap order relative to its parent. So we just do this thing again. 45 is greater than 50, or no, 50 is greater than 45, so we swap them. Ta-da. And then we also check 50 versus 60, but it turns out this is fine. The node is in heap order relative to its parent, so the insert operation in this case is done. And I think now's a good time to actually answer that question about duplicates. So say we wanted to add the value, value 39 to the heap. And in that case, depending on your implementation of the heap, like where you put less than or equal to and where you put strictly less than, 39 might get swapped with itself, might not, but after that, nothing would happen. These inequality signs are easy to lose track of. I distinctly remember with binary trees forgetting that they use strict inequalities, but I'm pretty sure heaps use non-strict inequalities. 39 and the evil twin, also 39, are in heap order because the parent node is greater than or equal to the child. Yeah, having equal elements just doesn't mess anything up. As another example, say you want to insert a duplicate of a value that exists elsewhere in the heap, say 57. So that would break heap order. 57 should be above 39. So we swap those two. 57 is now right here, still not in heap order. We'd swap these two. And then 57 would become the right child of 60. The fact that it is also the left child of 60 just doesn't cause any problems. And the data structure kind of sorts itself out naturally based on the time at which elements were inserted. Yeah, this is probably going to vary based on implementation, like two students' implementation of the heap that both get 100% might act slightly differently. But if you make your choices of which indices to use in other operations, then you might end up with a heap where if if two elements have the same priority, the tiebreaker is which element has been added to the heap first. And that's probably what you want in a real-world priority queue. So, moral of the story, duplicates are fine. I'm not sure if they're fine in the assignment question. They are fine in like the general data structure. So like, if anything I'm saying right now contradicts the assignment, follow the assignment. Because that might include some details about hotel booking or whatever that don't apply to heaps in general. So let's do some quick analysis of that. We see that at worst, the insert operation involves traversing a branch of the tree from leaf to root. Like, if we added an element that should be the new greatest element, we would have to move that element all the way up through successive swaps. Unfortunately, we can't skip straight to the root, even though it's totally technically possible with how we're using an array. That would mess up heap order, so we have to go one by one. But it'll still be faster than if we used a linked data structure, because array accesses are way nicer than pointer accesses. Even though arrays are technically pointers, it's weird. It's cool. So, as was hopefully made clear yesterday, any instance where you're traversing a branch of the tree from leaf to root, that is big O of log n. Traversing the entire height of the tree, that's going to do a number of traversals that is a logarithm of the number of elements in the tree. So since the height of the tree is big O of log n, and the worst case for the insert operation involves taking log n steps, the time complexity of the insert operation is big O of log n. And yeah, all of the checking and swapping is done using array indices, not pointers, and somewhere in your code you would have like size plus equals 1, because the heap has to keep track of its own size. I think I'm going to skip this example. The answer's on the next slide, so I still recommend studying from it yourself. It's just that there are 15 minutes left, and I want to tell you all about retrieve max, the other big operation for priority queues. So let's retrieve the max. It's right there. Cool. Heap ordering makes it so the largest element in the tree, so the element with the highest priority, is the root node, which is also the first element of the array. So like, I know the the priority queue ADT doesn't involve any sort of peak or top operation, but if it did, implementing it would be trivial. You would just return A index 0. But retrieve max involves like actually removing that highest priority element. Even if we were using a linked data structure, we'd still be a bit messed up. It's not immediately clear what we should replace this with. We don't want to just like sever these ties and like end up with two heaps. Wait, where am I? I want to keep that arrow. Cool. Yeah, the remaining subtrees are indeed heaps, but we want the whole thing to be a heap. So check out this algorithm. We're going to replace the root, so A at index 0, with the last item in the array. 30 used to be here, but has been promoted. And then we decrement the size. This step probably breaks heap order. In fact, I think the only case where it wouldn't break heap order is if you have duplicates. No, I can think of a case where this operation wouldn't break heap order without needing any duplicates, but let's not get into that. We need to fix this. And before I get into this, I just want to point out that this finally really takes advantage of the fact that we're using an array instead of a bunch of pointers to implement this. Like, finding the last element of the complete binary tree. If you were implementing this using like nodes and pointers and stuff, well, not only would the tree not be guaranteed to be complete, but if you assumed it was complete and then wanted to find the last element of it, you'd do something like current equals root dot right, and then maybe check both left and right and see which one has greater height. See that the left child has children but the right child doesn't, and then go to the right for that. And then just repeat that process of tentatively checking both the left and the right child, seeing which one has a greater height, and then like vaguely moving to the right. Doing that in a loop, that would take, well, a loop. And since it seems to involve traversing the height of the tree, I'd say it would probably be O of log n. But we know the array indices of specific elements of the tree, so we're able to just access that last element in constant time using the knowledge that it is at the last index of the array. Woohoo! To fix the array after we've broken heap order, we're going to do something that's sort of the opposite of how we moved up the tree, swapping elements based on how our insertion broke heap order. So like with this one, we checked 50 and its parent, and then its parent, and then its parent. This time, we're going to check its children. Earlier, we took advantage of the fact that nodes can only have one parent in a tree, and it was obvious what to swap, like what swap operation to do. We swapped it with the parent. But now we have two children to choose from. We want to pick a favorite. We want to figure out which of 30's children we should swap it with to eventually restore heap order. You might be able to figure it out, but I'll just give you the answer as usual. We're going to swap the root entry with the larger of the two child entries. So with 30, we compared it with 57 and 50. 57 is larger, so we're going to make that swap, ending up with 57 in the root, with children 30 and 50. And then we do this, continuing moving down the tree. It doesn't necessarily use recursion, but it definitely has recursion vibes because we are now focusing on this subtree. We do this process again, compare 30 with 52 and 48. 52 is the greater one, so we swap with 52. And then we'll need one more swap, comparing 30 with 42 and 12. 42 should clearly be swapped with 30. And boom. If it isn't immediately clear, definitely take some time later to think about why we chose the larger of the two children. I'll show you something that'll probably lead you on the right path. If we chose to swap 30 with 50 instead, then we would end up with 50 here and 30 here. And then we would keep swapping 30 with different elements of its subtree. I don't know, let's keep being stupid. Let's swap it with the lesser of the two children again. And then we'd end up with a tree that looks like this. Choosing the minimum child to swap with at each turn has done nothing to fix heap order. Could have seen this coming when we did the first swap. 50, 57, that's not in heap order. In order to maintain the property that the parent node has to be greater than both of its child nodes, it makes sense to swap with the greater of the two child nodes to ensure that the child node you bring up is greater than the one that you didn't. And as always, I'm gonna be real embarrassed if it turns out that heaps don't support duplicates, but I'm pretty sure the slide said they do. I just don't think about that sort of thing very often. But if we happen to have duplicates at the same level, you could just choose a child arbitrarily. The specific way in which you write your if statements for these algorithms will probably just end up enforcing a tiebreaker on its own. Hopefully it'll be the most recently inserted element, but not necessarily. Either of these swaps would work. Yeah, it totally says in an earlier slide that multiple entries can have the same priority. Like, I'm still paranoid. You could probably trust me, most likely. Very similar to the insert operation. Oh, yeah.
If the root has two children with the same values, the right side has less entries, would it be quicker to swap the back side? Because you don't have to traverse all the way down.
So if the, wait,
We swap with the right 52 rather than the left 52.
yeah. Yeah, totally. Because of how complete binary trees work, the right side will always have at most as many elements of the left side. So yeah, it would totally be smarter to use that that fact as a tiebreaker and just choose the right duplicate. Cool. Yeah?
So for example, like this is a complete tree, and on level 3, like we have 4 elements, right?
Wait, hold up.
Like,
Are we talking starting at 0 or starting at 1?
Yeah, so like
Well,
the one that starts with 42. So there are 4 elements, right? So
Mhm.
if we swap, and then we will end up one less element on that level. Like for example, if we don't have 28 at all,
yeah. So,
so will that break the heap structure?
I think I missed something that you said earlier. So, what did you say after noting that this has 4 nodes?
So if we try to swap on the right,
Mm-hmm.
so
Oh,
we-
like,
yeah, so we
like
will end
this?
up having one less element, right?
yeah,
So
definitely.
will that break the heap structure because we are supposed to get all the elements on the same line?
I don't think it will. Like, you're talking about calling retrieve max
Yeah.
on this tree, and like, we end up removing 57, swapping it with 28, and then moving it down the tree.
So like if 28 is not there.
So if we had the same heap, but 28 isn't there, and then we swapped 25 up here.
Oh, sorry.
Oh, does that answer your question, actually?
Yeah, all right.
Okay, cool. Okay, anything to say in the last minute of class? Probably not. Who has time to call retrieve max 3 times? Even though this will probably be a quiz question. Just stay put for a moment. I'm just checking the rest of the slides. Yeah, it's just the answer. And then, holy shit, Delta Room tomorrow. Yeah, that's it for this lecture. Hope you enjoyed learning about heaps.